Okay, so welcome everyone. Today's speaker is Robert Albaran, and he, after doing ground-based astronomical observation at Mauna Kea, he received a bachelor's in astronomy from University of Hawaii at Hilo in 2012, and he was a recipient of the 2011 NASA John Mather Nobel Scholar Award for research on the periodicity and localization of Saturnian kilometric radiation. And then he moved to Embry-Riddle Aeronautical University in Daytona Beach, Florida, where he did a master's for modeling spacecraft plasma interactions and density analysis of CubeSat wakes in Earth's ionosphere, followed by a PhD in engineering physics in 2022 for large-scale kinetic modeling of the ionosphere outflows observed by the Visions 1 sounding rocket. And he's currently a postdoc working as part of the CGS NASA Drive Center at UCLA, working on a unified magnetosphere modeling. And today he'll present on the modeling of ionosphere outflows observed by Visions 1 sounding rocket. So go ahead, Robert.
Thank you so much, Nick, and thank you all for being here today. So this is the bulk of my work for the last about 7 or 8 years or so at Embry-Riddle for the PhD dissertation. Kind of from the ground up, I developed a kinetic model with my advisor, Dr. Matthew Zettergren. And this kinetic model is really aimed to be very flexible and to kind of look at ion outflow from below 1,000 kilometers as observed by this Visions 1 sounding rocket, which launched in 2013 from Poker Flat Research Range in Alaska. So I'll be talking a little bit about the structure of my code and kind of the tests that we've done so far. So I'm sure everybody's seen a picture similar to this. The ion outflow is important because we're looking at mass loading of ionospheric plasma into the ionosphere. We have plasma sheet electrons that can get energized and ride geomagnetic field lines, precipitate, and of course create the beautiful displays of aurora that we see in the polar regions. But what's really important is the outflow loading into the magnetosphere, into the current region and plasma sheet regions, recurrent regions, and this can affect reconnection rates and just global responses of the magnetosphere. So of course the ionosphere is the neutral atmosphere ionized by extreme ultraviolet and X-rays from the sun. Primarily, there are 2 processes for ion outflow. We have type 1 and type 2 upflow, which generally occurs at lower altitudes, and this is just primarily ambipolar electric fields in type 2 and Joule heating from differential ion neutral drifts from type 1 ion upflow. And these 2 upflow processes bring ions to altitudes where BBLF and VLF wave powers can significantly transversely energize ions and achieve escape velocities. So what we're going to be looking at in this presentation is the upflow processes of ambipolar effects from electron precipitation, and also at wave energization. And we'll look at this wave energization in kind of 2 different ways, in both as coherent, resonant interactions, and also incoherent or non-resonant scattering in the transverse plane. So we'll look at that a little bit more in detail. This is just an example of ISCAT radar data showing the type 1 and type 2 upflow events. So on the left, we have type 1. So here we have the velocities up to about 500 meters per second. And this corresponds to electron temperature increases, ion temperature increases, suggesting differential ion neutral drifts and Joule heating for this type 1 event. The electron temperature and electron densities are kind of constant in that event, but then if we look at on the right, this is type 2, same parallel velocities at about 500 meters per second. and this corresponds to increases of TE and NE. So this suggests electron precipitation from the plasma sheet. Okay, so we have those upflow processes bring particles to higher altitudes where they're energized by waves, electromagnetic waves. There are a bunch of studies and observations via an outflow. Won't get into all that right now. But the modeling efforts really consist of fluid treatments of upflows that are good for thermalized plasmas, of course, below the collisionless transition region, maybe about 1,000 or so kilometers in altitude. With those thermalized plasmas, fluid treatments are good. At higher altitudes with less collisions, we see kinetic treatments. Even higher altitudes, they're no longer gyro center approximations. Sometimes they employ full Lorentz force particle trajectory simulations. Anyhow, in general, what some people do, for instance, the DYFK, the dynamic fluid kinetic model, it combines a fluid treatment at the bottom, about below the transition region, and a kinetic treatment above, and they kind of patch the interface here between. So a lot of semi-kinetic models have also simulated pressure cooker effects. So once particles are energized and to escape velocities, they can be reflected back down by parallel potential structures. And this makes pressure cooker effects. So these pressure cookers are responsible for ion populations of highly transversely energized populations in altitudes of low wave power, so at lower altitudes. And that's because they were reflected from higher altitudes where the wave powers were generally stronger. Okay, so then, of course, the Delcourt particle tracing codes were essential in looking at the escape of particles into the magnetosphere. So for our study here, what we wanted to do is to create a kinetic model from first principles that includes a mirror, gravitational forces, a self-consistent ambipolar electric field, a parallel potential drop structure, and a resonant and non-resonant mechanism for transverse wave heating. And we wanted to create a model that could connect easily to other low altitude models, kind of in that semi-kinetic treatment with fluid models. We also wanted to create a model that's flexible enough to handle curved field lines like many fluid models do. And we want to investigate these highly non-Maxwellian distributions corresponding to the observations by the Visions 1 sounding rocket. So the main question was, what are these processes that give the observations from the visions? So that's a problem we wanted to tackle. So I have this dipole magnetic field. Of course, in the dipole approximation, it's in 3 dimensions, but longitude invariant. We align the magnetic moment of the Earth along the positive z direction. We have the spherical coordinates and the dipole coordinates q along the field line. It goes from -1 to 1 at 0 at the equator. P is the L shell, so radially outwards, and phi, of course, is the longitude. So we can get an L shell, split it into all these little spatial bins. Each bin has volumes and metric factors and so forth. So this is really an interesting aspect of the code that I'll show a little bit later, but we can select different L shells and it has that magnetic field, and of course all the altitude dependencies with the gyro frequencies and wave powers and so on and so forth. So we can really investigate L shell dependent wave heating. So we populate these spatial cells just by a hydrostatic equilibrium solution. Of course, this is for a fluid treatment, but we're using it to initialize the kinetic simulation. We have a field-aligned gravitational term, G, and we get the density here. So this is NCQ, tilde is the spatial bin index. We normalize it by a macroparticle normalization constant mu, and here D3X are the spatial volumes. So for each Q tilde spatial bin, we can add up all the particles to get the total number of simulated particles. And we run this code on a MPI parallelized supercomputer architecture. So for mass loading purposes and simulations, the root rank, or the first processor, simulates total number of particles divided by, let's say, R processors, the first chunk, and then the next computer goes a little bit higher in altitude for the next chunk of its allotment of particles, and higher up in altitude for successive computers, and all the remaining particles are sent to the root rank. So this kind of balances the load of how many macroparticles are simulated by each computer. Of course, they talk to each other to gather statistics, moments, and the self-consistent ambipolar electric field. Okay, so the distribution functions are collected. Of course, we count the number of particles in each spatial bin, and then count the number of particles in each velocity bin. So we have two different modes in this simulation, or in this model. One is for two transverse dimensions and the binning of the particles. So we can bin along the magnetic field line in the V parallel, and we can bin it in the V perp 1 and V perp 2. And that's good for looking at non-resonant scattering and velocity diffusion, kind of just these electric fields that aren't gyro averaged. But then we can also look at the waves that are resonant with the gyro motion. And in that case, for the traditional wave particle interactions, as you might see, the binning is only in one perpendicular dimension. So it's just V perp. So of course, V perp 1, V perp 2, they add in quadrature to get V perp, but that's just an interesting feature that we can have here. So what I'll show you in what follows is actually binning in two transverse dimensions. So this would be for incoherent scattering of particles in velocity space from these electric fields that don't have phases or wave phases equal to the gyro frequency. So this is how the particles are initialized. We take a three-dimensional Maxwellian distribution in Cartesian coordinates in the global Cartesian system. We transform Cartesian to dipole coordinates in the field-aligned coordinate system via spherical coordinate transformations. We get the field-aligned coordinate V parallel, and that's responsible for all translational motion. So all forces on the particles are in the parallel direction. So everything except wave particle interactions or just drifting Maxwellians. So this is the parallel velocity. The P and the phi coordinates of dipole coordinates are now the V perp 1 and the V perp 2 directions. So we initialize the two perpendicular directions with, in the absence of transverse energization by any turbulence, these perpendicular directions just drift. They don't really get energized. They don't change. It just, the first adiabatic invariance is conserved. So the bottom altitude spatial cell has an injection of ionospheric ions to balance out this hydrostatic equilibrium issue. So in kinetic theory, we don't have pressure gradients like thermal pressure. Really, it's a thermal distribution, Maxwellian, that has their velocities, and that makes the pressure. But there's no real pressure gradient force like in fluid theory. So to have hydrostatic equilibrium, we needed to supply that balance of pressure. So we inject particles from the lower boundary on time steps equal to the mean thermal particle transit time through the lower boundary GO cell. So the GO cell is not a computational cell. It just gets densities and things like that to set the boundary conditions. So we have this influx of particles from the lower boundary. Particles can leave the upper boundary and lower flux tube boundaries and re-enter the simulation domain on time scales within tau I. So tau I, this is the injection time step. So HQ, DQ, this is just the ghost cell field aligned dimension. So particles can come in, they can come out. Every time step of tau I, we compute the distribution functions in moments. So we also recompute the total number of particles, see how many particles left, see how many particles came in, and track the total number of particles, and so on and so forth. For the time steps, the time step here is H, and this is what's interesting is that we don't have to resolve the gyro period, because this is a kind of like a gyro-centered approximation, but instead we can't have the time step really, really big, because what happens is these particles are updated by RK4 and three Cartesian coordinates, and all forces are along the field line. So the particles will overshoot the field line, and then they'll get pushed back on the field line, and then they'll update their new position and offshoot a little bit, and then kind of get projected back on the field line, and so on and so forth. So in that process, if the time step is really large, those overshoots become significant. The numerical approximation isn't that robust anymore. But we also have to limit or resolve the interaction time of particles in these wave fields. So if a particle is very fast and it just zips through this, region of wave activity, and we don't resolve that in the simulation, then of course we don't get much dynamics. So tau I here, this is the interaction time of particles through the wave field. So generally, our simulation time step just resolves that interaction time, tau I, or excuse me, tau perp, the perpendicular interaction time. Okay, so these are now field-aligned forces all along EQ. We have gravity, of course, projected onto the field line. We have the ambipolar electric field that's self-consistent. So N here's the density. Every injection time step, we compute a new set of low-order moments and distributions. We get the spatial gradient of density, and that updates the ambipolar electric field. So I'll show you some tests where N is active and when it's static. Really, when it's active, it just pulls things towards regions of low density. And here we have an ad hoc electrostatic potential barrier to reflect particles that are less than some certain parallel energy. So this is just kind of a field-aligned, monotonic increase of potential in altitude. Of course, the altitude profiles of these electrostatic fields, these parallel electric fields, are not well defined. There's a lot of research into that, but we can, put hard reflections, make different altitude profiles. But I'll just show you some basic ones today. So with wave-particle interactions, like I said, we can update the particles along two perpendicular directions or just one perpendicular direction. Instead of one perpendicular speed, we can break it up into two perpendicular velocities. And for non-resonant scattering, we can see the diffusion along those two perpendicular velocity components. For coherent interactions, it goes down to the one perpendicular speed. This term here in the diffusion coefficients, d perp, so I is for 1 and 2, so d perp 1, d perp 2, those two different directions. This psi perp 1 and psi perp 2, these are the fractions of wave power in each of those two dimensions. So if you were to go from a non-scattering in these two dimensions, or excuse me, non-coherent interactions in these two dimensions to coherent interactions, this psi perp 1 goes from 0.5 to just 1, and you just have one, d perp instead of d perp 1 and d perp 2. And then in that process, this 2 changes to a 4. But anyhow, you can there's a lot of literature of the resonant interactions, not too much in the non-resonant interactions. But the main idea is that we have a velocity here, v perp 1, and it's updated by this delta v term to get a new velocity. And this delta v term depends on tau perp, so that's the interaction time of particles through the turbulence wave field. It depends on the parallel velocity and the field-aligned arc length of the turbulence, ds. Because the regions, the localization of these turbulence fields aren't very well understood, I'm supposing ds to span the entire flux tube, so the entire flux tube is resonant. But as the particles are energized in v perp, by increasing v perp, we increase the gyro radius, and if the gyro radius exceeds the perpendicular wavelength, then we get this self-limited heating term. So at high altitudes, if the wave powers are high enough to energize v perp beyond the gyro radius, and the gyro radius goes above the perpendicular wavelength, there's a saturation in the perpendicular heating level. And that's the effect of finite gyro radius heating. So, of course, that mirror force converts perpendicular motion to parallel motion on adiabatic cooling rates. So we form the distribution functions, the lower order moments, that's sort of standard. So here's some test cases for the kinetic equilibrium. The initialization of the hydrostatic approximation kind of then experiences a departure into what I'm calling the kinetic equilibrium as opposed to hydrostatic equilibrium. And this is after about maybe 20 or 30 minutes of where the system kind of reaches a steady state. So we do some cases, Maxwellian distributions here in the v perp 1, v perp 2, and v parallel planes at initial time and 2 hours later. It's conserved, looks good. So on the top left here, we have a static ambipolar electric field in this panel. It's just the initial density profile to compute the ambipolar field. So everything kind of falls down initially due to gravity, and then the thermal injection from the lower boundary has these cold ionospheric particles here, and then it eventually balances out. But you have some sort of transient, event leading into that equilibrium. So the idea of the active ambipolar field, we have the injection, so it makes a density gradient near the bottom, which makes a stronger ambipolar field, and plasma starts falling due to gravity and then is lifted up due to this active field. These are just Maxwellian distributions, again, in the v parallel, v perp 1, v parallel, v perp 2, and v perp 2 and v perp 1 planes. So this is resolving in 2 perpendicular directions. So we get this v perp 1 and v perp 2 bird's eye view, which is pretty neat. Down here, with retaining the 2 perpendicular directions, we can then reconstruct 3-dimensional pitch angle, energy, and gyro angle distribution functions as seen here. So alpha is the pitch angle, E is total energy, and theta is the gyro angle. So here, everything's initialized isotropic, so no preference in parallel or perpendicular directions. So, and same here, everything's pretty isotropic in the gyro plane and the pitch angles. And then these planes, then the alpha theta planes, it just becomes isotropic after some time. Okay, so then we can increase the electron temperature periodically throughout the simulation as a kind of rough and simple way to model electron precipitation. So we ramp up the electron temperature. Here is NS versus T, the total particle number, at these different delta TE rates of 0.26 K per second, 1.28 K per second. As the ambipolar electric field goes up, the total upflow, brings plasma up. So then the injected particles from the lower boundary can fill up the domain, and we have more total number of particles. So it's just kind of a general upflow. The parallel distributions, you see they kind of shift parallel to the positive direction. So that's what I've in convention going higher in altitude. So these are just some active ambipolar electric field cases with these upflow events. kind of this Maxwellian gets smushed upwards in the v parallel direction. In the plane perpendicular, it's pretty much always Maxwellian. And these pitch angle distributions show towards 0 degrees, so that's outwards. 180 degrees would be going downwards. Okay, so we have these upflow plume events, leaves behind this cold population of plasma. We have these parallel velocities. Nothing too exciting. Of course, these are very low altitudes, as you can see. So this is mostly kind of testing our code, showing that we get hydrostatic equilibrium in these non-reactive plasmas. So this does not include a mirror force, for instance, and things like that. But once we have equilibrium due to ambipolar electric field, gravity, and the thermal injection, after the transient has propagated out, we have kinetic equilibrium, and then we can start introducing extra forces like the mirror force, parallel potential structures, and transverse heating. So with different L shells, if we change an L shell to a more extreme one, let's say L from 5 to L15, the magnetic field at a given altitude is greater. So that means that the gyro frequency at that given altitude is greater as well. So that means that these particles are exposed to lower wave powers. So there is a heating dependence on the L shell. That is something that's not, I guess, too common in other codes, especially kinetic models, looking at the curvature of L shells and looking at wave heating in different L shells by the dependence of gyro frequency. But anyhow, here's some test cases for L is 7.88 RE. We have the upflow, well, the parallel an ambipolar electric field and the wave particle interactions. These are just comparisons to the DYFK model from the Zhang 2006 study. So here are the distribution functions for wave particle interactions. As we can see, at this time, at 9.6 minutes, at 3,000 kilometers, we get a little bit of transverse heating, so it gets smushed out perpendicular, and then adiabatic cooling kind of takes this perpendicular motion and brings it into parallel motion. So we get a little bit of a bowl at later times. After we kind of get the steady state, we can see the low perpendicular velocity bins evacuated, and it makes these toroidal distributions, or these bowl distributions. So they get brought up into these bowls, and they look like these toroids in the plane perpendicular, or these ring distributions, as they're also called. So that's kind of similar to here. These are mostly conics and bowls, not too many toroids for this study. But you can look at my dissertation and look at all the details if you're interested in more detailed comparison. So then we also look at wave heating at short wavelengths. So as the perpendicular wavelength goes below the gyro radius, then the perpendicular heating rate gets saturated. So what that means is that when the perpendicular wavelength is infinity, or long wavelength approximation, we get all of these wavelengths to energize the ions. So there was a study by Barghouti et al. 2006 that tested these different perpendicular wavelengths, and what they found out was that perpendicular wavelength at around 10 kilometers is characteristic to the observations at 4.8 RE equatorward of the cusp. So generally, the idea is simulate a lot of different perpendicular wavelengths, see which one corresponds to observations. But now, of course, with more advanced studies and observations, we're starting to get an idea of what these perpendicular wavelengths should be, and these turbulent structures in general, and their variations in space and time, and with what wave powers and so on and so forth. So at infinite perpendicular wavelength, we don't have any limited heating, so we get these very well-defined bowl distributions. When we limit the perpendicular wavelength to 10 meters, of course, that reduces the transverse heating significantly, as we can see here. So now we simulate some pressure cookers. So we have the energization from BBELF and a parallel potential structure. So everything kind of gets slammed down by this parallel potential structure, downward potential drop. And so only particles with high enough parallel energy can overcome the electrostatic barrier and inhabit high altitude. So really what these barriers tend to do is filter particle populations by parallel energy and altitude. So we have this parameter h as well, which is the computational time step that is said to resolve the particle interaction time with the turbulence field. The WU 2002 study looked at pressure cooker effects. They looked at the differential anisotropic ratio, if I'm not mistaken. So pretty much they're consistently computing a parallel potential structure by looking at the different values of perpendicular and parallel electron and ion temperatures. So that's where this field is created. You know, if we have a pitch angle distribution of electrons and ions that have different mirror points, then they can have these unrealistically large space charges. So these electric fields kind of neutralize that. But anyway, the WU paper in this study of DYFK computed that self-consistently, whereas we just kind of put on these different altitude profiles, as you can see here. But of course, this is an open parameter that hopefully in the future we can get more constraints on. So these pressure cookers we see at when we do have this parallel drop on the bottom left, on the top left, we do not have a parallel potential structure, only heating, and we get higher parallel energies at a given altitude for these pressure cookers. So the idea is that we have these transversely accelerated ions that are lifted up by the mirror force and then reflected back down. So these pressure cookers explain these high transverse energization levels in regions of low wave power. Okay, since we're almost short on time, I'm just going to kind of run through real quick. So these are some distributions. We see these on the bottom left, these bowl distributions form from wave particle interactions, and then these parallel potential structures kind of drive this whole bowl distribution downwards in altitude. So the VISIONS case study, I'll just show you some results real quick. So this was a sounding rocket that was launched in February of 2013 from the Poker Flat Research Range in Alaska. It was equipped with 2 miniaturized imagers for low energy neutral atoms, or the Milena instruments, to remotely sense ion outflow by imaging ENAs from about 50 eV to 3 keV. It was also equipped with an electrostatic ion analyzer and a fields and thermal plasma instrument to look at DC electric fields, electron temperatures and densities, and so forth. So this rocket was launched into the expansion phase of an auroral substorm, and it goes up to about 700, a little more kilometers in altitude, and is to look at the ion outflow drivers below 1,000 kilometers. Traditionally, we think of these electromagnetic wave regions to be at higher altitudes, or just generally these BBLF turbulences at higher altitudes. But there's, especially from more recent studies like the VISIONS 2 rocket, which was launched in 2019, it showed that there's significant wave activity at much lower altitudes, like 300 to 400 kilometers altitude. Anyhow, so for this VISIONS 1 flight, I parameterized my model by the initial density and temperature, reference density and reference temperature from the Poker Flat ISR data. So we can parameterize the initial ion scale heights and injection temperatures and densities and so forth. at this position in the flight. So as this rocket flies, it goes through many different L shells. So we're concerned with kind of an instantaneous position to simulate that L shell. So at that position, at that time of flight, we see this wave spectra recorded by VISIONS. So this is in the whole time of flight. So it's kind of active in this area here. So generally at low frequencies, we have a higher wave power. So at higher altitudes where the gyro frequency is less, the resonant interactions are with higher wave powers. And these usually follow a power law fit. We did a best fit to get a power law index, so this chi-perp term at about 2.1. But of course, this is at this time of flight, a little bit later and a little bit later, this spectra kind of changes around. So this should be taken with a grain of salt, really, for these reference wave powers and gyro frequencies. But anyway, with that spectral index and wave parameterization, I then submit some different simulations for different perpendicular wavelengths and reference parallel electric fields. Kind of similar idea. We have these upflows and these outflow events at the initial plume. The parallel electric field kind of suppresses that, so it looks like it reaches kind of a pseudo equilibrium by these competing forces. And we get these kind of toroid distributions in one direction, in perpendicular one. The distribution functions kind of get evacuated at the low perpendicular velocities. We get these toroids, ring distributions, as we can see here again. With these parallel potential structures, we also get these counter-streaming populations where some of them are mostly transverse, and then we have this outflowing population as well. But then we look at the VISIONS data, and here on the top right, we have the downflowing ions. So these are the differential ion energy fluxes sorted by pitch angle. So downwards, transverse, and upward flowing. And as we can see here, at this time of flight, this was near 700 kilometers, nothing is really going up that flux tube where the rocket is. Everything's kind of coming down, and we have this very strong transverse population. So this suggests that things are transversely energized at high altitudes with high wave powers and then brought down by strong parallel electric fields to match these. So really, when modeling these distributions, it's two-piece. First, we look at the transverse levels, what conditions of wave energizations are necessary to give these levels, and then what are the parallel potential structures and these transverse energization levels responsible for giving these downward flowing flux levels. So that's kind of the idea. So we have these counter streaming populations. I simulated different interaction time steps, different pressure cooker parameters. And then I sort it similarly in pitch angle, so downwards, transverse, and upwards. So for these altitudes, about 700 kilometers at the VISIONS altitude, we're not getting flux levels in transverse or downwards nearly as close as what VISIONS is observing. So of course, we're seeing all these things coming from above the rocket. So instead, now I shift the simulation domain higher up in altitude, up to about 2 RE or so, and increase the wave powers, the reference wave powers and reference parallel electric fields to get these pressure cooker environments for these different interaction times H. And simulating these different pressure cookers, we can kind of get an idea of the general conditions that could give these observations from VISIONS. So at these high altitudes, we have these wave powers energizing populations in the transverse direction, and then these parallel electric fields driving these bulge distributions in their entirety downwards. And we see this kind of low parallel velocity distribution, the secondary distribution in here. And so if we recreate the pitch angle, gyro angle, and energy distributions from the phase space distributions in two perpendicular directions, then we're getting a lot of information on the gyro angle. But of course, it's kind of redundant with the incoherent scattering because it's always isotropic in the gyro angle. But that's a feature that could be explored later. Anyhow, so with these pressure cooker conditions here, the general idea is that at these high altitudes near maybe 2 RE or so, we get wave powers that can give transverse heating levels consistent with those recorded by visions. And then we look at what could bring those transversely energized populations down to 700 kilometers, where the rocket is. And so that's kind of a way to parameterize the parallel electric field. So with this simulation here, with these parameters, we get transverse levels up to 50 eV energy bins, fluxes up to about 2 times 10 to the 12 EV per meter squared per second per steradian. So with these conditions here, we're modeling actually this region of the observations of visions. So we have these transverse guys that peak higher flux levels than the parallel, and these downward flowing guys here, and nothing's upward flowing. So it actually matches really well with these parameters that I simulated. So that's the main point. Really, we have this magnetospheric plasma transport of particles that are transversely energized at wave powers that are much stronger than those at the Vision's rocket level. And these populations are transported down to the rocket by strong parallel electric fields. So in conclusion, this is a study that introduces a new kinetic model on large-scale computational resources. And we can look at these highly non-Maxwellian distribution functions such as boles and conics and toroids form by either resonant or non-resonant scattering in 1 or 2 perpendicular transverse dimensions. We can simulate different flux tubes. We account for the curvature of the flux tubes in the dipole approximation. And when studying the Visions case study, we see that to give the observations, we need wave heating of ions that's well above the Visions 1 rocket. So we need energization of particles at much higher altitudes where there are increased wave power spectral densities. And then these are brought down by parallel electric fields. And the important part is that we have to remember the constraints of the model. We have a lot of open parameters, such as the reference parallel electric field, the altitude profile of this potential structure. Does it have a hard reflection at some altitudes? What's the shape of that in altitude? Also looking at the perpendicular wavelengths. What are the variations in space and time of these perpendicular wavelengths and these given wave powers? How do they change along the flux tube? So these are open parameters that I hope to see assist in constraining these models. So it's a very exciting time because we're actually getting observations to constrain these parameters. But yeah, so that's pretty much my presentation. Please feel free to look at my dissertation here online. It has all the details. And if there are any questions, thank you so much.
Okay, thank you, Robert. Does anyone have any questions? You can either raise your hand, speak up, or type into the chat. Well, while we're waiting for others, do have one question. it was slightly unclear to me with the observations from the sounding rocket. Was that sort of an unusual or unexpected that it was all sort of downflow, or could
Yeah,
you maybe give a bit more context there?
sure. Yeah, that's an excellent question. So here we have the downflowing, transverse, and upflowing. Yeah, so traditionally we think of these transversely accelerated ions to give outflowing conics. So they're transversely energized, and then the mirror force brings them to higher altitudes. So that is, I believe, generally the consensus. Well, the first idea of looking at conics and bowls and things, we typically think of them going outwards. So this was rather unique, I suppose, in that regards, that these are bowl and conic distributions that are highly transversely energized, but they're going downwards. So really, this is, I suppose, just looking into the mechanisms of pressure cookers and how they can give transversely energized particles in regions of low wave power. Yeah, so and that's something that we can simulate later, looking at the altitude profiles of the potentials, the reference potential structures, see if they have interesting features along the field line, and then looking at the parameterization of the turbulence interactions with particles.
Okay, thanks. Yeah, I just wasn't. That's what I thought it was unusual, but I wasn't sure. And I guess with one experiment, you don't know, or one observation, you don't know how common this is, or if it was very unusual.
Yeah, that's something, I guess, yet to be observationally discovered. But yeah, as those observations come in, a model like this can kind of fortify our understanding of what's going on.
Are there any other questions? Bill, go ahead. Bill, do you have a question? I'm not sure. Bill, you raised your hand, but we cannot hear you. Bill?
Yeah, finally.
Okay, go ahead.
I had to leave halfway through, and I've been doing this on my iPhone. So, but Robert, I just wanted to ask, could you say anything about how you think convective transport enters into the heating, the ultimate heating that these ions get? And by that, I mean, for example, if this heating is taking place in the cusp region and the ions are being transported horizontally through the cusp to a limited extent of perpendicular or a limited extent in, say, latitude of heating. How will that affect the results that you're talking about, or have you considered that?
Yeah, that's an excellent point. So there are a couple of things. So one is, it goes back to the localization and variations of these wave fields. So that could be. So I don't have convection for these. But what we can do is model, different flux tubes, but they'll all be stationary. So the idea would rather be get a region on a flux tube, let's say in the cusp, for instance, or in an area where we have some interesting wave activity, and then attempt to kind of localize that region along the flux tube. So maybe the particles can go through some altitude that has one spectrum, another one maybe with a different spectrum, and so on and so forth. That could be one way to attack this, but in terms of the convection, that would be a feature that would hopefully I can add some time in the future.
Okay, that's kind of what I figured. I just wanted to get your take on it. Thank you.
Thank you.
Are there any other questions? If not, then thank you again, Robert, for a nice presentation.
Thank you so much, everybody.